I'm going to be rambling about B-epsilon trees and write optimization. It's a paper I read and I loved it, so I'm going to talk about it a little bit. So why this paper? Well, usually when putting together a talk, the hardest part of putting together a talk is figuring out what order you present things in and how you lay things out so that everyone can really follow along and understand it. This paper was well-written, clearly structured. Everything was in the right order, and really all I did was go through section by section and go, yep, that part makes sense to put here. Then I do the next part, then the next paragraph, and just go through. And took me not too long to put together the slides. I don't actually remember how long, but it was easy because the paper just flowed. So that, but also the paper was really useful. This is not the paper that I'm talking about, but it's something that I submitted to the IWP9 workshop. It is a paper about a file system I wrote. That file system was written using B-epsilon trees. So these are something that I've actually used in my hobbyist work. And they've kind of ended up being just the right data structure. So not only is it a nice little paper, the structure that they're describing turns out to be a pretty useful thing. So enough about that, though. I'm not going to talk about my file system anymore after this. If you want, come to me after the talk, and I'll happily ramble about it all to you. I'll talk your ear off about that some other time. What I really want to talk about here is B-trees and the paper that I'm presenting. So it's a paper with a lot of authors. And it's not an original chunk of work. So the original paper for describing the data structure was initially proposed, I believe, in, right there, 2003, in the Symposium of Discrete Algorithms, where there was a much less lovable paper with a much less evocative title, Lower Bounds for External Memory Dictionaries, which I read that and go, what? Sorry. But it is not a new paper or a new data structure, but it is a new paper that kind of ended up in Usenix and kind of pushed the data structure into the consciousness of the computer science world, as far as I can tell, which is really the important thing. So this is kind of describing what a B-epsilon tree is, initially proposed by Brodel and Faberberg as a way to demonstrate asymptotic performance trade-off curves between B-trees and buffered repository trees. I'm going to say buffered repository trees really aren't on the topic list for today, but they're kind of, what if you just have a hierarchy of buffers? So B-trees, I'll review what they are, but they're basically read-optimized buffered repository trees are write-optimized, and B-epsilon trees are kind of a way to turn the knob between write optimization and read optimization. Oops, where was I? Okay, so again, B-epsilon, and this, because the paper was good and I feel like it needs to be featured in the slides, so most of my slides are screenshots of the paper, which gives you a talk with the vibe of a ransom note. Anyway, so it's a write-optimized data structure that can be used to organize on-disk storage for an application, such as a database or file system. It provides a key-value API similar to a B-tree, but with better performance, particularly for inserts, range queries, and key-value updates. So unpacking that a little bit. It's write-optimized. What does that mean? Well, it's optimized for writing to disk. On disk, so that means that comes with a lot of implications and assumptions. If you've got an on-disk data structure, it needs to deal with blocks rather than with arbitrary ranges of data, arbitrary seeks. It needs to avoid I/O operations because the data is far away. For a database or file system, gives some of the use cases that the authors had in mind. Key value API, I hope everyone knows what a key value API is here. and like a B tree with better performance, which kind of gives you the performance profile that people are thinking of. So on disk comes with the assumption, so you're on block storage, high latency matters, caching matters. And caching is kind of the, well, okay, so the model for disks, they're far away, but they're not that slow. So requesting some data is going to be a lot of latency as if you're on spinning Rust, as the disk head seeks to the right location. You're looking at tens of milliseconds. On SSDs, it's better, but you're still looking at orders of magnitude slower than main memory. And even with SSDs, sequential access matters, although this data structure really doesn't address that. And that, which means that caching matters. So because you want to actually avoid all these IOs, you need to be able to keep your data local in a way that, and avoid going out to disk over and over again. So write optimized, obviously, this data structure is focused on optimizing write performance. And the other thing that this paper says is that they clearly lay out their goals. After finishing this article, a reader should have the basic understanding of how a B epsilon tree works, its basic performance characteristics, how it compares to other key value stores, so there are comparisons here, and how to design applications to gain the most performance from a B epsilon tree. That last sentence kind of has a few implications. Specifically, if you just take code that was designed for a B tree and move it to a B epsilon tree, it will not be optimal. So again, just summarizing the goals here. Summary of how the things work, how they compare, and how to use them. And the other nice thing about this, there is a link in the paper to a GitHub repository. There's code that you can download, compile, and run. You don't have to rely on some hand-wavy descriptions of how to do things or some pseudocode to figure out what's going on. You can actually just go and read the code. Can we please have more papers do this? So, okay. So we're going to go into the API and basic structure. It's a B tree-like tree for organizing on disk data, illustrated in Figure 1. This Figure 1 will eventually show up, I promise. So it's a self-bind. So I'm going to take a step back. The paper doesn't talk about what B trees are, but I think that they're important to understand. So if you're going to go through any more of this. So here we leave the paper a little bit, take a detour, and we'll get back soon. So B trees are a self-balancing non-binary search tree, or an n-ary search tree. If you've got, and here's a diagram. You've got this tree covering keys sparsely from the range of 3 to 37. The root of the tree has 2 children. This guy has 3 children, and then the last guy has 5 children. You know, fairly normal. Each one of them points to several, all paths through the tree have the same height. If a node has n children, it contains n-1 keys. So, for example, if you've got 3 children, you've got 2 keys here. Each key bounds the node, the children of the node. So the keys constrain the range of each child. Every node except the root is at least half full, and that's one of the properties that you use for balancing the tree. The root is the exception. It either is a leaf node, so you have a single node tree, or it contains at least 2 children, because if you had a single node in the root, you could just go down a level, and because there's only one place to go, you go down a level and delete the root. And then the inner, and I just already mentioned that the inner nodes bound the child's values. So to use it, looking it up looks similar to a binary tree. You start at the root, and then while you're not at the leaf, you either, when you reach the leaf, you return the value. If you're not at a leaf, you look up the child, load the node for that value. So looks very similar to a binary tree, except instead of if the key is less than the value, go left, otherwise go right, you do a binary search to figure out which child to walk down Insertions are slightly more complicated. You start by finding the node you want to insert to. So this is pretty similar to a lookup. You do the walk down to the leaf. If there's room in that node, you just append to it or insert into the right location, so binary search will find it. If not, then you split the node and insert the new key that used to be the middle value into the parent. If this, of course, expands the parent node, so if you run out of room, you split the parent, and you keep going up all the way to the top of the tree. If the root node splits, create a new root node that points at the at the new split of the root. And because of the way that you're only growing from the root, and you're growing both halves of the root at the same speed, things are always balanced. So that's kind of how you keep a binary tree or a B tree balanced. To delete, okay, so example. In this case, you're looking at the old tree here, except in this node, starting off, you have 11 and 12. So the simple case, we're inserting 13. There's room, so it goes right here. That's it. Going to the split of a node, if the node fills up, you go from 11, 12, 13. Now you have 13, 14. It's full, and you split the node. And now you've got a new key here that says 13. OK, deletion. That's a bit of a can of worms. And as is tradition, most papers, most descriptions don't really talk about it and just say exercise left to the reader. So I'm going to move on. OK, I'm lying. I'll talk about it because I took the time to put together the slide. So it's basically the opposite of insertion. If a node gets insufficiently full, so the invariant that we mentioned earlier is not satisfied, if it's not half full, then you attempt to merge. So look at the neighbors. If one of the neighbors has enough room that you can just shrink the nodes and collapse the two nodes into one, then you copy the data over and delete the neighbor. Otherwise, you want to do a rotation, which means pull over some of the data from one node into the other one and try to get the sizes approximately equal. If a merge happened, well, there's a key now that no longer points at a node, delete it from the parent, recurse up the tree. If you delete one of the children of the root node that has two parents or two children, you're down to one node. The root node is now useless, throw it away, and your tree is also shrunk by a level. So that's basically what a B tree is. And I think that's good enough of a understanding for this talk. So B epsilon trees. Now we get to the real meat of the talk. What is a B epsilon tree? What's different? So the distinguishing feature of a B epsilon tree is that internal nodes allocate space for a buffer. This buffer is used to store messages which encode updates that will eventually be applied to leaves. So this is the figure one that was promised so long ago. If you look at the buffers and erase them, it looks exactly like a B tree. But then what you do is you add in a buffer, and it becomes this right-optimized data structure. It's a really small tweak. The leaf nodes still just have elements. They don't need a write buffer at all. But the inner nodes all have a write buffer that contains messages for delayed updates. So what's in a message? Well, you can have different operations. So the very basic one would be you want to insert a new key, you insert a create message. And the create message goes into the roots buffer. You want to delete a node? Well, you don't go down to the leaves and delete it. You insert a deletion message into the root node's buffer. And that will basically say, hey, when you walk the tree, the value in the leaf that you found, ignore it. It's deleted. Mutations, this is kind of where the right optimization starts to really come in. If you want to modify a value, you don't need to read it back before you modify it. You can just insert a mutation for the value into the tree blindly, and when eventually it'll get applied. Or you can do your own custom things. So why? I think this covers it. Moving messages down the tree in batches is the key to the B epsilon tree's performance. By storing newly inserted messages in a buffer near the root, a B epsilon tree can avoid seeking all over disk to put elements in their target location. B epsilon tree only moves messages when enough have accumulated to amortize the I/O cost. So basically, moving messages in batches. What you do, you insert into the root node until the root node is full. So you have your root node, you toss a message into it. So create value, create value, create value. And then when the root node is full, pick a victim node and basically say, hey, I've got 10 messages going down this path of the tree. Let me flush down that path. So you pick the heaviest child and move the messages down in a group to that node. The downside of this, well, okay. So the batching like this reduces the number of I/O operations because, well, first off, if you're touching the root node all the time, it's almost always going to be in cache. You're not seeking around the disk to find the random leaves that you're modifying. Most I/O operations, in theory, can be done in, or most writes can, in theory, be done in a single I/O operation with some amortization in there. The other thing, which isn't mentioned in the paper, but I think is worth calling out, this plays extremely well with copy on write. So because you are copying the root node to make the modifications, to do the upserts, you're only doing one copy for every I/O operation instead of walking down the tree to the leaf, copying the leaf. Now you've changed the leaf's pointer, so you now need to copy its parent, modify the parent's pointer, now the parent's parent, all the way up to the tree. So you can reduce the amount of write amplification by an order of magnitude. The downside is that you rewrite messages multiple times as you do this, as you copy them down the tree. Turns out that in practice, this isn't really a problem. So that's the write optimization that we're talking about when we talk about a write optimized data structure. To look things up, you pay a cost and complexity. And actually getting this right in my implementation was one of the harder things. Because it's fine if you're dealing with a tree that's not being modified concurrently or not being read as it's being scanned. But it gets pretty hard once you actually want to allow concurrent scans and writes to the tree. So all the messages, you've got messages on the path from the root node to the child. Nicely enough, there's no issues around, well, what if it's on the different path? It's always on the trace along the tree. So you walk down to the leaf and then find the value and then walk back up to the root, applying the messages that are buffered for that key. This can be short-circuited sometimes. For example, if you have a creation or a deletion, you can stop walking down to the leaf early because, well, you've already got the final value. You don't need to do any mutations on the way. And the nice thing here is that there's actually no cost for this, asymptotically at least, because, well, if you're walking to the leaf, you have to do the I/O. If you're assuming that the cost of doing the I/O is very high compared to the cost of computation, which is an assumption you see all the time in this kind of data structure, this kind of disk-based data structure, which, side note, NVMe, NVRAM, and so on, this may be becoming less and less true, but at the time the paper was written, this was a very true assumption. So basically, any computation that you do on the nodes is almost negligible compared to the cost of I/O. And if you're doing a B tree, you've already done all the I/O to get down to the leaf node. Why not do the application on your way back up? So there's a bunch of complexity in actually implementing this, but there's no cost theoretically. Gotta love theory. Okay, so when talking about this, I just mentioned the number of performance assumptions. For the analysis, which is the next slide, in theory, just to make all the math work out nicely and get rid of a whole bunch of weirdness in there, they make a bunch of simplifying assumptions. Specifically, for the for the equations on the next slide, they were done under the assumptions that all key value pairs were the same size. If you want to use different ones, it's definitely doable. It's just left as an exercise to the reader. Each node is accessible with a single I/O, so you're not seeking around disk and reading different chunks on disk. It's just one sequential read. And each I/O is roughly equally expensive. So with that, this is kind of the comparison in performance from the paper. If you look at the cost of a B epsilon tree, The most general case is where you have epsilon as some variable that you can tune. So epsilon is actually I should have mentioned this. Epsilon is essentially the ratio that you split between buffers and pivots. So how much of the tree is dedicated to write buffering versus fan out to the children. The most common case for that, because the numbers work out nicely, is if you set epsilon to half. So if you have, say, an 8 kilobyte or 8 megabyte B epsilon tree node, you can split it in half and use 4 megabytes for write buffer and 4 megabytes for pivots. B trees are, when you basically set epsilon to 0, you end up with the B epsilon tree becoming a B tree, and everything falls out nice. LSM trees, log structured merge trees, they are kind of not the classic paper, but you see something like that in LevelDB or other popular database key-value databases. And LSM plus BF is log structured merge tree with Bloom filter, so you can filter out which levels you're looking at. Because the problem with log structured merge trees is that there are multiple places that a value could be, and you don't know which one it is until you actually try it. Bloom filter lets you eliminate most of those statistically by just kind of having a probabilistic filter for these. This is where the value could be. As you can see, basically the B epsilon tree with epsilon as half is basically the same performance for all reads as the B tree, but is faster for inserts. And the bigger the B is, the nicer that actually happens. B is the size of the leaf. And there's another little neat trick they pull here, where because of the way that you've got write optimizations going, and you're not doing a ton of IOs for every output, it turns out that B epsilon trees actually like really big nodes. So multiple megabytes is actually not a crazy thing to see. Especially if you're doing all the caching for the root node and you're not actually flushing it to disk on every IO. Or you do some, I think TokuDB does this, where they basically they violate the assumption about each IO is equally expensive and each node is accessible with a single IO, and they split the nodes into pages, which are not necessarily all sequential. Don't quote me on that, though. I haven't read their code. Okay, so then the last part of this is really, how do you use these effectively? Well, thankfully, the paper has a section on this. We've got a section on how to speed up applications by using a B epsilon tree. As I alluded to earlier, it's not just a drop it in and everything gets faster, though it is a drop it in and nothing gets worse. The tree gets slightly taller because it's narrower, but things keep working more or less the same. So what you need, so the two words that kind of cover how you make things faster using B epsilon trees are blind writes. Just do a blind write and everything will be good. At this point, I probably should say what a blind write is. It's just when you toss a mutation into the tree without actually looking at the value. So for example, when I'm writing my file system, a prime example would be the wstat operation. Wstat is basically, well, when you have a directory entry, so a file has a name, and that name maps to a entry that has an inode, an owner, a modification time, and a whole bunch of other metadata. So if I wanted to touch a file, basically what I'm trying to do is to update the modification time to now. I don't need to read any of the metadata. I don't need to know what the old modification time was. I don't need to know who the owner was, subtleties aside. There's very little I need to know. So I can just say, hey, let me just toss a write into the data structure, and eventually it'll get updated to this thing, and I don't actually care what the old values were, and I don't need to read anything to do that. It's just a dumb write. Or, for example, changing the owner. I can set the owner name with the current UID, and that's fine. Except, again, permissions. These are always kind of a pain in the ass. You might not be able to do blind writes all the time. You have to be a little bit careful. In a file system, you end up with a dcache, so the directory cache, and you can kind of, and you can look into the directory cache and say, and do the permission check on cache data instead of doing a whole bunch of I/O to read the data back. But it's hard sometimes to actually take full advantage of this, which is, again, why this is a caveat. And then there's also the other downside. The data store actually needs to know about the data. So in this example, the B epsilon tree needs to be aware that this is a directory entry with a modification time and an owner. So you have to actually have a way of teaching your B epsilon tree data store about your application level data structures. Maybe it's a callback table. Maybe you're just writing your own implementation and you can just specialize it. Maybe you're doing some other customization, but you do need to teach your data store about the data formats to actually get the full benefits. So, of course, no paper claiming performance metrics is complete without performance metrics. So I'm not the only one writing a file system with these. The research group that actually published this paper is also doing their own file system called BetterFS. And if you ask, why didn't I use it? Well, theirs is very much a research prototype with all that implies. Mine is not even that. So they have their file system and they compare it to other file systems including ButterFS, which is built with B trees. And they kind of do a quick sketch where they go through their sweet spot, small file creation. And BetterFS does, what is it, an order of magnitude better than the comparison XFS. Their closest competitor to XFS, significantly better than, almost 2 orders of magnitude better than ext4. Although that's a really small number for ext4, so this is probably on slow spinning Rust. And according to them, ZFS crashed halfway through the test. I'm surprised by that because ZFS is generally a pretty battle-tested file system. Who knows, maybe they just ran out of RAM. I don't know. But that's kind of the numbers. And here's the other benchmark on reading, actually, where they're grepping through the files. And you can see that BetterFS is significantly faster than pretty much every other file system for this. I've got some theories on this because this is a slightly surprising result. I think the reason for this is that they were testing a whole bunch of small files. And in a B epsilon tree with small files, you end up with most of the data in the write buffers. And the write buffers is already pulled in just when you scan the tree and list the data. So again, this is the theory. I haven't gone through and replicated it or checked into why. But that's my personal theory for a slightly surprising result. This paper isn't perfect. There are a few things I disliked about it. For example, when I said that deletion was not covered in traditional B-tree documentation or write-ups, this paper is no exception. They follow that tradition very closely. The code that they have does have deletion, but the paper doesn't describe it beyond saying, well, yeah, you toss in a delete operation and eventually it reaches the leaf and you delete the value, just like in a B tree, except there are other complications that they completely gloss over. So in a B tree, when the node hits half size, you merge it. In a B epsilon tree, what if there's too much data in the buffer? How do you flush that out and make room? Do you flush it out and make room, or do you relax the constraints? Because flushing it means now you've made copy and write a lot worse. You've done a whole bunch of other stuff. There's a bunch of trade-offs that you can make here, and it's not clear what the best ones are. I would appreciate a bit of guidance on how to do that from the paper rather than needing to reinvent the wheel myself. Copy and write is something that I noticed, but isn't really called out clearly in the paper or called out at all. And then the last thing is that, yeah, they've got a nice file system-based comparison, but there's a lot of stuff that goes into a file system. There's so much other ancillary stuff, like how do you allocate the blocks on disk? And all of that affects how the performance ends up shaking out. So it would be really nice if there was an apples-to-apples comparison where, for example, they have their B epsilon library. What if they crank the epsilon all the way to one edge or the other and see how, and benchmarked how that worked? Or potentially they could have done some comparisons against best-of-breed B tree libraries or LSM trees and gotten a comparison that actually was at least a little bit more isolated. So those are kind of the things that I didn't like about the paper. But overall, I really liked it. BetterFS was kind of another thing that came out of the research group. I think it's worth taking a look at their papers. They've got a lot of them, and a lot of them are pretty similar quality. So if you have a lot of time, I recommend you go to the website, pick a few of them. I think the one at the top, sorry, not the one at the top. The last one at the bottom, the right optimized file system, is actually a really good one. There's also the, oh, okay, good, my cursor does show up. So the, this one's got a great title, Writes Rot Right, another file systems, and that's another good paper. And there's one I'm looking for, I might not have screenshotted it, about, oh, no, here it is, optimizing every operation in a right optimized file system. So these are the ones I would also recommend people read if they're interested. Beyond that, I think that's basically everything I have to say. If there are any questions, feel free to ask, and I will do my best.
The epsilon trees are as good as a B tree for everything except inserts in which they are better. When should I not drop the epsilon tree into something that's built for a B tree?
When you can't do blind writes. Because the thing is that you get, well, so I think there are two reasons they're not more widely used. One, this paper came out in 2015. A lot of the code that would use a B epsilon tree is already out there, and it was written before they were well known. But the other thing is that you do need to teach your B epsilon tree about your operations. So you can't get, they are a slightly worse B tree, just a little bit worse because they're narrower and taller and you're wasting a bunch of space on buffers that don't get used effectively if you are going for something and just dropping it in.
How did you end up implementing deletions?
How did I end up implementing deletions? So there are two things. There's one paper from, I'm blanking on the name, the person behind ButterFS, the Linux file system that is a couple of years away from production ready and will be and has been for the last several decades, or the last decade. They had a paper on how to implement copy on write B trees, the traditional ones, with a bunch of proposed relaxations on the balance. So I did a combination of, well, flush down a path, but not too much, so that you're not screwing up the so you're not screwing up the copy on write optimizations. But then, on the other hand, with those relaxations, you can, there's also, make sure that you're flushing a little bit extra so that you can, on the next time you touch the node, you're guaranteed that there'll be enough space that you can actually do some copies and merges and rotations without modifying too much else. There's a lot of little tricky bits there, and there's a lot of little tricky bits there, and I don't remember all of them or all of the subtleties. So I would need to pull up my code. Yes?
Do the buffer commands work like a look aside, or are there actually
Do the buffer commands act like a look-aside, or is there actually code there? So that's up to the implementer. I would not put code there myself. For me, I mean, the way it makes sense to me is that you basically would have a table of opcodes, and then so each message has a message type. Do this operation. You look that up in a callback table, or just hard code it in, and do a switch statement on them on the final apply.
And this goes to your needing to know your structure so that you're actually changing fields, not just writing blocks.
Correct. This goes back to knowing the structure. Yep.
One thing I didn't understand in production, it said that it's better performance in the B tree for range queries, but I didn't understand what element gave that.
Yeah, that's one thing they claimed, and I'm not sure entirely why they're claiming that. There is a slight improvement possibly because you've got people tend to insert stuff related to something pretty early on or in batches. So it tends to end up clustered in the tree. But I think that's a bit of a reach.
The thing with range queries is that B is typically much larger.
Yeah, right. B being the size of the nodes might be a lot larger as well in a B tree, or in a B epsilon tree than in a B tree, because you're trying to. Again, it feels like it's a little bit of a reach, but it makes sense, kind of. Trying to see if there's anyone over in the back there. Nope. Okay.
If you're reading and applying a bunch of operations, do you apply the result back? Because if you didn't, then I can imagine a worst case would be like you've written a bunch of stuff and they just remain in buffers, but then you repeatedly read from one piece. You're constantly like applying all these changes that hadn't been flushed back to that.
You tend to hit that. Yeah, you don't flush them down usually. There are a bunch of heuristics you can apply, and they mention some of them in the paper. For example, if you get a ton of writes that are directed to a specific leaf, so updating the same key over and over again, the implementation of B epsilon trees that they took from in TokuDB will have a heuristic to notice that and just immediately write that to the leaf. I am not sure of the details of those heuristics, but there are definitely heuristics around improving some of this. And the simple version that you write actually ends up performing pretty well, but there's a lot of tweaks you can do and a lot of complexity you can put into this to try to optimize things as much as possible. Yep.
Early on, you mentioned concurrency, but I don't remember seeing that in the paper. Is that something you encountered in your implementation?
Yeah, that is one of those things where the paper. Question is concurrency. I mentioned it, but it wasn't in the paper. Correct, it's not in the paper. That's one of those things where when you take it to real world, you realize there's stuff that's not mentioned in the paper. There's a few neat properties that you get with just copy and write in general, where you can do something where a reader can not block the writer and the writer can not block the reader because you're copying everything over. Reclamation gets a little bit tricky in that case, so I'm using a variant of RCU around there. And then there's just, at that point, if you have someone doing a large scan, how do you avoid holding too much of the tree open? And there's no rocket science in there and no crazy algorithms. It's just, you look at what operations can happen concurrently, put in the right locks, which, again, copy and write means you don't need very many locks. Decide what trade-offs, like, for example, if you're doing a directory scan in a file system while deleting files in a directory, it doesn't matter if, it is okay to skip over a few, kind of, because that's they're going away anyways. So you get a consistent view, but then as you kind of iterate the scan and delete some stuff, you just re-walk the tree if something changed under you. Engineering, not computer science, I guess. Yep.
Maybe you mentioned this, but could you give some examples of custom messages?
Sure. In the examples I used was basically updating.
Oh, that's
Yeah. So for example, if you're updating the modification time of a file, that would be a custom message. If you're updating the owner of a file, it's a custom message. If you wanted to change for example, if you're implementing a database with bank accounts or with integers, just storing the amount of, storing a value, you can apply a delta to the value rather than trying to read the data, subtract something from the key and write it back. So increment could be done as a blind write rather than a read, modify, write. Yep.
So, same question, but LSMs. If I have a log structure merge tree based system,
Yep.
why shouldn't I drop a PFC tree in place of log structure merge tree?
Read performance. Yep. So B-epsilon trees are basically slightly better theoretically on the read side because you're basically hitting, you're doing slightly better on the read side than on the, theoretical performance for it is slightly better.
Well, yeah, so this seems to imply that I should always drop it. PFC. Oh no, for the point queries. Okay, I see.
Yep, for the point queries. I think that, again, I'm not sure if, I have to think about the trade-offs. Log structure merge trees do let you do some interesting stuff with varying, they can take advantage of storage hierarchies better because you can, because you've got the strata there. So, yeah, exactly. Yes.
Epsilon equals to half. Isn't the read performance of LSM trees better than the B epsilon tree because it's twice that of an LSM tree?
With LSM trees, I think the thing that costs you is figuring out where to find the data.
I was talking about the complexity.
Oh, let me think. Yeah. So let's see. Sorry, I'm having trouble hearing.
I'm saying if epsilon equals half, isn't the point query with no upserts performance of B epsilon trees worse than a log structured merge tree with Bloom filters? Because it's 2 times log n base B for a B epsilon tree versus just log n base B for LSM tree plus Bloom filters.
Possibly. Let me think. I'm sorry. You might be right. We'll talk after. Yeah.
I think it's a constant factor. So it just
Yeah.
points out and it's asking for it.
Yeah, it is a constant factor, but yeah. Yep. Sorry, could you speak up?
Have you seen any comparison of B plus and B star trees?
No, although I think this paper is kind of using B trees in the general family sense. So if I remember, B plus has the values in the leaf nodes, which seems to be what this is assuming. So, and then, and yeah, and I don't remember what the B star tree tweak was. Sorry? Oh, share memory with neighbors. Yeah, okay. So that's definitely, yeah, it would be interesting to see. I don't think they have a comparison. Okay, I think we're good.